There are a lot of factors that led to my decision to always eat Oreos with my trusty Oreo consumption kit. I'm able to get a full dunk without getting my fingers wet.
Oh, jeez!
I don't spread germs from my hands to the Oreos. And everything just tastes better with official Oreos branding. But my composite and multi-factored cream and cocoa cookie consumption contemplations aside, good news. I still have 12 Oreos left. Here's a bit of math. 12 has a lot of factors too. The factors of a number, like the factors of 12, are the positive integers that multiply to 12 with no remainder. The factors of 12 are 1, 2, 3, 4, 6, and 12. We can think of factors using division as well. These are factors of 12 because 12 divided by any one of these numbers is an integer with no remainder left over. 12 divided by 1 is 12, 12 divided by 2 is 6, 12 over 3 is 4, and so on. We say 12 is divisible by its factors. Of course, 1 is a factor of every number, and every number is a factor of itself, since we can multiply any number by 1 and we get that number. Many numbers have more factors than just 1 and themselves, and these numbers are called composite numbers, like 12, for example, or 9, or 4. Composite numbers are for what are known as losers. So if those lame numbers that have more factors than 1 and themselves are composite, what numbers are left? Those would be the numbers that are only divisible by 1 and themselves and have no other factors. These are prime numbers. We call people who talk about prime numbers mathematicians, or chads. What factors does 3 have? Only 1 and itself, so 3 is prime. What about 5? The only factors of 5 are 1 and 5, so it's prime. What about 2? Only factors are 1 and 2, so indeed 2 is prime. Of course, no other even number can possibly be prime because every other even number has at least 3 distinct factors: 1, itself, and 2, since it's even. How about 1? Is 1 prime? Its only factors are 1 and itself, so yes? No!
It's not prime. In the past, many mathematicians did consider 1 to be prime. G.H. Hardy's textbook, A Course in Pure Mathematics, first published in 1908, included 1 as a prime, and 1 does fit the definition of prime we gave earlier, but the actual definition of prime number we use today excludes 1. We say a prime number is an integer greater than 1 that is only divisible by 1 and itself. Alternatively, we could say a prime number is a positive integer with exactly 2 distinct factors. This would also exclude 1 because 1 only has one factor, namely 1. So why the change in definition? Well, that's a bit of a long story, but we can point to one of the most important theorems in mathematics for a little clue.
There are a lot of mathematical phrases that I just don't think people say often enough. For example, every time I hear, "Math and music are actually closely related," followed by no explanation whatsoever, well, let's just say I like it. Another one I really like is,
"The prime numbers are the building blocks of mathematics."
I really wish people would say that more often too. This common shorthand metaphor is how a lot of people explain the fundamental theorem of arithmetic, without actually saying the words fundamental or theorem or arithmetic.
With a name like that, you know this theorem is important. The fundamental theorem of arithmetic states that every integer greater than 1 either is a prime number or has a unique factorization into primes. For example, 12's unique prime factorization is 2 times 2 times 3. We could shuffle the order of these primes around, but we cannot make 12 using different primes. This is in contrast to a factorization of 12 into
composite numbers, which is not always unique. For example, 12 can be factored into 4 times 3 or 6 times 2. We're able to factor 12 in multiple ways when we allow composites, but there's only one factorization into primes. That's why we say the primes are the building blocks of mathematics, because every integer greater than 1 either is prime or has a unique factorization into primes. So why isn't 1 prime? Well, what happens to the fundamental theorem of arithmetic if we say that 1 is a prime number? It completely breaks. Before, we had that 12 was uniquely factored into these primes, 2 times 2 times 3. No 1, no problem. But if 1 is prime, our unique factorization goes out the window. Now we could factor 12 into primes like this, 2 times 2 times 3 times 1, or 2 times 2 times 3 times 1 times 1, or 1 times 2 times 2 times 1 times 1 times 3 times 1. The possibilities are endless. This is because 1 is the multiplicative identity of the integers. Multiplying a number by 1 doesn't change it, so we can include as many 1s as we want to get infinitely many factorizations of any integer.
Oh geez, when does this factor tree end?
We could just modify the statement of the fundamental theorem of arithmetic so that it's true even if 1 is a prime number, but it's theorems like this which lead us to suspect 1 should be something different from the primes, something perhaps even more important, and so primes have to be greater than 1. We already knew that 1 wasn't a composite number since its only factors are 1 in itself, but now we know it isn't prime either, and so the fundamental theorem of arithmetic holds, and that theorem is why we say the primes are the building blocks of mathematics.
Honestly, I'm not impressed. I mean, primes are cool and the fundamental theorem of arithmetic is cool, but it seems kind of obvious. By definition, an integer greater than 1 is either going to be prime or composite. If it's composite, then we could factor it into numbers other than 1 and itself. Maybe those factors are prime, maybe they're composite. If they're composite, we could factor those down too, and just keep going until we get a prime factorization. And that prime factorization is unique. Okay, that part's pretty cool, but it's not so easy to impress me. What impresses me is infinity. Are there infinitely many primes? It seems kind of hard to imagine the answer being yes or no. If there are only finitely many primes, that means after a certain point, every number afterwards is just a product of the finite set of primes that we're already familiar with. That seems impossible. On the other hand, if there are infinitely many primes, could it really be that even after a quadrillion numbers, primes keep popping up after that aren't products of any of the previous numbers? Neither possibility seems easy to believe, so to answer this question, what we need is a proof.
A court must show someone is guilty beyond a reasonable doubt to convict them. But in math, to prove a statement, we must justify its truth beyond all doubt. A mathematical proof definitively establishes the proven claim. And in fact, one of the most famous early proofs in mathematics is a proof about whether or not there are infinitely many primes.
The proof was given by Euclid around 300 BC in his legendary textbook, The Elements. This is considered the second most widely printed text ever, behind only the Bible. His proof went something like this. Oh, sorry, just always like to set the mood before this proof. Wouldn't want to waste the moment.
If there are finitely many primes, then we could list them out like this. p1, p2, and so on through pn, the last prime. Euclid's brilliant idea, the key to this proof, is to use this list of primes to construct a number that isn't divisible by any of them. Consider the number p. Start by defining p to be the product of all the primes. So p equals p1 times p2 times p3 and so on up to pn. Of course, right now p is divisible by all the primes, since we've created it by multiplying all the primes together. The magic happens when we add 1. So now we're defining p as the product of all the primes plus 1. Clearly, p is bigger than all of the primes in our list, and since we assumed this is a complete list of the primes, that means p itself can't be prime. Thus, p must have a prime factorization by the fundamental theorem of arithmetic. However, now that we've got this plus 1, if we divide p by any prime number, we get a remainder of 1 left over. This means none of these primes are factors of p, and so p can't have a prime factorization. This contradicts the fundamental theorem of arithmetic, since this contradiction arose from our assumption that there are finitely many primes, there must in fact be infinitely many primes.
No!
At the end of a proof, mathematicians like to put what we call a tombstone, just a symbol signifying the end of the proof. Typically, this will just be a square or a diamond, but it can be anything. I like to use Oreos to end my proofs. We just saw an example of a proof by contradiction. We prove the claim by assuming that the claim is false, then demonstrate that leads to an absurdity, or a contradiction. Thus, the claim must be true in order to avoid the contradiction. We just did something really cool. We proved there are infinitely many prime numbers. We're flirting with infinity, and that's pretty awesome. But we did cheat a little bit because we used the fundamental theorem of arithmetic in our proof, and we didn't prove the fundamental theorem of arithmetic. To be fair, we didn't use the whole theorem in our proof. We didn't use the uniqueness of prime factorizations, we only used their existence. We'll save the proof of the fundamental theorem for a rainy day, but sometimes we have to indulge in the pleasures of making a leap of faith, taking a theorem for granted and getting a glimpse of the beauty that lies just past it. And now we know, no matter how high we leap, no matter how far we look, we'll never see the end of the primes. But outside of math, do primes and composites really matter? I mean, whether I've got a prime number of Oreos or a composite number of Oreos, I'm gonna eat the Oreos. What do I do?